Okay, it is time for us to start. So let us welcome Ting, who will now lead the hands-on part of the MSstatsTMT discussion.
Okay. Hi. I think the next time for today we will talk about the tutorial of MSstatsTMT. So in order to do the tutorial, we need first download the the dataset on our screen. Same as before, if you go to the Google Doc for the second part. Okay. Then there is a highlight link, which if you click into the link, there is a zip file. So, and then download it into your local computer. If many people are downloading it at the same time, it may be a little slow. And after you download it, open it. So like my case, I open it and unzip it and open it. So this is a folder called MSstatsTMT May Institute 2021. In the folder, the script we will use is MSstatsTMT analysis for PD output. And then open this R script. I assume like after the first 2 days lecture, most people have already installed R and R Studio. So, okay. After you open, that's the file. I also assume you have already installed MSstatsTMT. If you haven't installed that, in the folder there is another R script called installed required package MSstatsTMT. You can open that R script and just run. You can select and run all of them. Okay, I can install it again. So select them and run. It will install MSstatsTMT. And again, as before, we say if here, select N, type N, and then nothing. Okay. So if you installed MSstats and MSstatsTMT, and you tap MSstats here, you can see because I have installed like several MSstats family package, but that's the package MSstatsTMT. It means you have already installed it. The version is 1.8.2. That's what we need. And after you install the package, then we can start the analysis. Okay. So first, let's have an overlook. Let's have an overview of MSstatsTMT. If you go back to the MSstatsTMT analysis for PD output script, R script, and run line 12, this will I think you. Oh, sorry. First, we should library MSstatsTMT, which just load the MSstatsTMT into your R Studio session, and then if you run the question mark MSstatsTMT, it will show you, give you an overview of MSstatsTMT. Here, it shows what functions MSstatsTMT provides. They are MSstatsTMT similar like MSstats because it's a family. They are family package, sibling package. So there are 4 types of functions MSstatsTMT provide. First, of course, is the converter. There are actually 4, but here only lists 3 converters. You can tell it from the name. The PD to MSstatsTMT format is the converter for PD, and then maxquant to MSstatsTMT format is the converter for maxquant. And we also provide 2 converters, which one is for SpectrumMan, is a package software developed by SpectrumNow team. And another one is for just a very new converter for OpenMS. I haven't listed here. In today's lecture, I will cover how to analyze the data output from PD using MSstatsTMT. But I also provide the file about a tutorial file about how to analyze the output data from maxquant. So after the class, you can refer to it if you use maxquant data. And that's the first type of function, converter function. After this function, this function will just convert different input data format data files into the one required input format by MSstatsTMT. And the second function, as Olga mentioned in her lecture, is protein summarization, which summarizes the PSM level data to protein level data. And then similar like MSstats, MSstatsTMT also provide visualization function for quality control. And then last one is, of course, the core of the package is to perform the statistical testing, which called the group comparison TMT. We will start from okay, so the first step, then let's start the analysis. Of course, the first step is we need to read in the input files. This tutorial is using the protein discoverer data. Okay. Also, if you look at the folder, there are 2 HTML. The 2 HTML, one is for maxquant output, one is for PD output, and so each of both of them will introduce how to use MSstatsTMT to analyze the data step by step. So for today's tutorial, the dataset we use is this dataset. So the dataset it's a control mixture dataset. So where we spec in the UPS1 protein into a constant background with 4 different ratios, concentrations. So the 4 concentrations is 0. Okay, maybe you have a question. Sorry. We have some question here. Oh, okay. So someone asked how I think Tobias asked how to install MSstats. If you install this MSstats, if you open the install the required package R screen, this code will install MSstats and MSstatsTMT both. So the dataset
and Ting, quick question.
Yes.
So this the PD data is not normalized in PD, right? So just original.
Yes.
Yeah.
Yes. This is not non-normalized data. So the dataset design is like this. We spec in the UPS1 protein with full concentration. The full concentration is 0.67, 0.125, 0.5, and 1. And inside each mixture, there are two 2 replicates for each concentration, and then there are totally 8 replicates. So someone asked, I think I remember we have a question is why we use 2 reference channel here. I think for this specific data set is really because we make the design balance, then we have 8 sample, 8 replicates, and it's 10-plex TMT, so we have 2 remaining channel, and we just use the 2 empty channel as reference. If your design only has 1 remaining channel, I think it's okay to use 1 reference channel. We internally compare, the normalization based on 1 reference channel and the 2 reference channel. Actually, there is a very small increase, and this increase, I think, probably not very worse. It's not worse to use another another channel for reference. So my recommendation is if you reference channel is enough for most cases. And then for each mixture, we have 8 replicates and 2 reference channel. For this case, we run technical replicate run. So also we have a question before is we indeed run the same material into the mass spec several times to estimate the technical variation. So if sometimes there's also technical replicates run also take lab resource. So sometimes we will maybe have a trade-off between technical replicates run or fractionations. If you can have enough lab resource to do most, then that would be great. But if you can only do one, either technical replicates or fractionation, I think I would say fractionation may be a better choice to increase the proteome coverage. For this case, because when we designed, we didn't consider that fractionation, so we do the technical replicate MS run. We prepare 5 such mixtures, and each mixture has 3 technical replicate runs. So there are totally 15 runs. And this data set was analyzed by PD 2.2. The input data we need is the PSM file from PD. So the data set we use here, okay. So the data set we need from PD is a PSM file. In PD, you can select what you want to output, what level data you would like to output, peptide, PSM, or protein. What we need is the PSM file, which is not normalized PSM level data. Actually, here what we use is intensity, not ratio. We prefer MSstatsTMT prefer to use the reporter and intensity data, not ratio as input. Actually, we are also working on currently what we are working on is to see whether we should extend to the ratio and what's the different performance difference using ratio and intensities for PD data. So currently this input is, if you run it, read the input, raw PD, and if we see what's the data, if you look at input data, the data here is intensity. That's what we prefer to use. And then that's inside PD PSM file. What we need some important columns we need the peptide sequence column, annotation column, and we also need the protein protein ID column. PD in PD it can provide multiple protein ID options. For example, the one is first one is master protein accessions, which select representative proteins for the protein group. And we also have protein accessions. Protein accessions may include several protein together as a protein group if the proteins are not distinguishable. And protein master protein accessions select represent protein from the protein groups. In MSstatsTMT, you can select which protein ID you would like to use as the final protein name. Someone also, I think we also have a question yesterday is what's the protein name you would like to like? Can we select some like gene name? MSstatsTMT currently just take the protein ID column from data processing tool like PD as protein name. So if they don't have, if the tool does not provide the gene name or other as protein name, so MSstatsTMT is unable to use that as protein name. But if like PD, if they have gene names, then you can use gene name as your protein name. So that's the protein name. Next thing, very important column is spectral file. In this spectral file, this spectral file column just tell us the run ID. That's the first run we have. In this data set, we should have totally 15 runs. So if we check unique peptide, if we check the, it should be spectral. If we check how many unique runs in the data set, there are 15 runs. Because as we mentioned, as we just see before, so before there are 15 runs. So in the files, in the PSM files, it has totally 15 runs. And then next, the last one is the most important is the intensity column. We have in this data set, it is 10-plex TMT. So we have 10 columns for the 10 channels. I think previously we have a question is ask whether because here is the channel isobaric tag for 10-plex TMT. I think one student asked whether they can use their own isobaric tag which is different from TMT tag 10-plex, 11-plex, or 16-plex. Yes, I think as long as you have this file format column names, you can use it because MSstatsTMT does not assume certain isobaric tags are used. We just we detect actually MSstatsTMT check the annotation file and to see what the users gave the tag name, the tag ID they use in their experiments, and MSstatsTMT select the corresponding intensity columns. So which means if you have 170C, such as that, and you tell MSstatsTMT in the annotation file that your isobaric tag is 170C, then MSstatsTMT will just select that columns. So that's the PSM file, and then the first tab, the first input file we always need is the data file, which includes the intensity data. And second one is the annotation file. The annotation file, let's first read in the annotation, and let's see what the annotation file includes. there are 7 columns in the annotation file. I know it seems scared because there are you need to fill in all the information for 7 columns. In particular, I think our many users confused about the technical replicant nature and fraction, what these 2 columns mean. In this tutorial, I will first assume that we have already had the 2 input data, the 2 intensity file and annotation file, and then we will go through the analysis. In the last part, I will use half hour to, because that's actually is the first and almost maybe also the biggest difficulty most users faced when they use MSStats is how to prepare the annotation file. I will later I will spend a half hour to teach how to prepare the annotation file for different designs. For the designs which has fractionation or technical replicates, I will have different. I will use different examples to show how to prepare this annotation file. So if you have questions about this annotation, such as what does the technical replicate mixture mean, or what does the fraction mean, you can keep it later. I will explain it in more details. So currently, we just assume you have already had this annotation file, then we can continue the analysis. So after we have the 2 input data PSM file and annotation file, let's check. This is just a preliminary check. How many proteins in the input file? If we run this one, it will tell us, okay, there are 50 proteins. This data set is a toy example I created for this tutorial. Because the most commonly we see there are thousands, and for some very deep fractionated data set, it may have more than 10,000 proteins. But for that proteins, if we run the whole workflow, it may take half hour for protein summarization and group comparison. So I just select 50 proteins from the dataset as an example to run through the workflow. Okay, then that's why this dataset only have 50 proteins. And in this dataset, I use the protein excitation as a protein ID. So among the 50 proteins, we know this dataset, it has spec-in data. We also want to check how many spec-in proteins. And then there are 15, so there are 15 spec-in proteins. When in the database, if it's a spec-in protein, I give a special name, UPS, put UPS in the protein name, indicate is special proteins, and we expect those proteins are differentially abundant across different concentrations. So they are among the 15 proteins, there are totally 15 differentially abundant proteins. And also we can check how many peptides it has. There are around like 460 peptides. So the last one is we can also, we see, okay. So we can also, like before, we can check how many spectral file, and we confirm there are 15 runs. So, and the run name usually is what's your raw spectral file name. So you can check whether they are consistent with your raw spectral file names. So okay, now we are good to go. Since we already have the PSM file, the PSM files, reporting and intensities, and we also have the annotation file, which tell us what the channel is, what the condition is, which is required for our following group test statistical testing. So the next step is is first run converter to generate the required input format. What the converter does is, let's see, because it's PD output file, so we will use the PD to MSTMT format converter. In the converter, that's the function, the converter function. It requires two input. One is input, and the second is annotation. It's a two required input, and also it has several options. For these options, I think the most important and you may want to change for your own data set is which protein ID you would like to use. So like here, I use a protein accession, but if you want like a single protein ID, you may change it to master protein accessions. So that's probably when you run your own analysis, you may change this option. It's the protein ID option. And the others is just to remove some low quality proteins, such as same as MSStats. You can also remove the one hit wonder proteins, which has only one peptide ions, or you can also remove the sometimes we know it's very few, but sometimes within one mixture there may be some missing channels. It's very few, rare, but sometimes it happens. You may want to remove those PSMs, peptides, which has missing channels within each run. Okay. So if we have the PD if we run this this converter, let's run it. You'll see is this message tell us what the converter does inside it. Okay, I think we have a question is I can briefly answer it, but I will have a detail introduction later. Is what's the key point in PD annotation file? In the annotation file, it's always the key information we need is because in the raw intensity file, what we know is the sample is each PSM and the reporter intensity of the peptide ion in each sample, but we don't know the information about the sample. For example, what's the which condition, which group the sample comes from. So we need an annotation file to tell MSstatsTMT what the condition and what the condition the sample comes from, what's the phenotype information of the sample. So this information is required for the downstream statistical testing. I will give more details later for the annotation file. So go back to the converter. Inside converter, first thing we check is here. We check whether there is shared peptides, and we will remove the shared peptides, and then also we will remove the features, the peptide ions, which have very few intensities. Even it's very this case is very rare, but sometimes happen. We want to remove it, and then we will aggregate the spectral level data to the peptide level data. If the data set, for this data set we don't have fractionations, if the data set have fractionation, then the converter will also combine the fraction. So yeah, here is for this parameter remove few measurements within one run is the case here. Few means one or two. So if, for example, it's a 10-plex TMT, but for some PSM features, it only has one or two channels out of 10 channels. This is very rare, but sometimes happen like here, there are 7 such features. Then we would like to remove such features because if it only has 1 or 2 intensities, even we want to remove input for such features, it's very hard, because it's very hard to use only 1 or 2 data points to input the missing 8 or 9 data points. So for such features, imputation will not work, so we will just remove such features. And then after, let's see the output of the converter. So that's the output of converter, which is also the required input format for MSstatsTMT. You may have currently we cover 4 converters for full data processing tool for TMT experiments, PD, MaxQuant, also OpenMS and SpectralMan. But we are also working closely with FragPep lab. They will also give a tutorial this Friday to develop the converter for philosopher or FragPep. But you may also use some your in-house software, which we don't have converter. Then if you want to use MSstatsTMT, the input format you need to prepare is like this. So that's if you want to use protein summarization and the static testing function in an MSstatsTMT, then you probably need to prepare such a input file. Yeah, so as I mentioned before, we don't assume MSstatsTMT does not assume the number of channels in the input data. So it's the user tell us how many channels you have. So you can use so MSstatsTMT can handle like 6-plex, 10-plex, 11 or 16, or TMT Pro, which is 16-plex the TMT data. So in the input, this output converter, it has information, it's protein name, peptide sequence, and the charge, and PSM, which is the peptide N. And then the information is mixture, which tell us how many, which tell us what's the TMT mixture ID, and the technical mixture tell us whether it's a technical replicated MS run or not. And then it's a run ID, also channel ID, and the condition information, biological information, and most importantly is the intensity, as the raw intensity information. So all this information here is is from the annotation file. So tell us the channel in condition and the bioreplicate, similar like MSstats. So okay, if I think we have a question. Okay, that's a good question. So can we remove or ignore the unnecessary TMT channels from analysis? Yes, we can do that. We have the option to do that. You can do that in the annotation file again. So if you look at again the annotation file, we have a channel. Maybe I should explain more that here is we have the run information, we have the channel information, and then the condition tell and bioreplicates are just 2 columns tell us the phenotype information of the channel and the run. We have keywords here for condition. If this channel is used for normalization, it's a reference channel, then just put a num here. If it's an unnecessary channel, you don't want to use it later, you can just put empty here. It's a keyword empty, then MSstatsTMT will just not use that channel for the analysis because it's empty, nothing here. So let's check again that so that's again, that's the output of converter. Then let's check the how many proteins in the converter. Again, it's 50. That's what we input. And then how many proteins is spiking proteins is 15. Then okay, now we have the we have our format, good form data file with good format. Then we can start the real analysis, statistical analysis. The first step is we want to summarize the peptide level data to protein level data. As Olga introduced in her lecture, is we will use TMP MSS summarization to summarize it. Let's first see what the function looks like. So MSST protein summarization function here. Protein summarization function here. It has first is data is the output of converter, which this one input PD, and then method is the protein summarization method. We MSstatsTMT provide 4 options. First is MSstats. Second is median polish, and then median and log sum. So many people actually ask what's the difference between MSstats and MSstats polish. If you remember, if you did the tutorial, attended the tutorial yesterday, is here MSstats because MSstats option, what it does, it call the protein summarization function in MSstats, which is data process function to perform the protein summarization. And in MSstats, data process provides functions such as imputation and feature selection, and also TMT median polish summarization. So you can understand simply, you can understand MSstats equal to median polish imputation plus median polish. So it's a first impute a missing value within each run, and then use median polish to perform the protein summarization. If you don't want to impute, then you can just directly call median polish. That's the difference between MSstats and median polish is the imputation option. And currently we don't allow to the function to do feature selection, but in the future, if because it's still a DDA experiment, so they are not allowed of features, so we think feature selection is not very helpful here, so we don't have the feature selection option. But in the future, we may have we may use the feature selection option in MSstats. So that's the second option is the method. Then we have the 4 options. The default is MSstats, which first impute missing value and then run median polish to perform protein summarization. And another thing I would like to point out here is we do the media imputation and protein summarization for each MS run separately. So for example, this case, it has 15 runs. So then we will record we will do the protein summarization 15 times internally for each run separately, because we think the 10 channels, all the channels within one run, they share very similar technical bias. So it's but across the mixture, actually we can see a quite big shift, and then we would like to do the protein summarization within each run. Then another 2 important feature parameters is the normalization parameters. MSstatsTMT provide 2 normalization options. First is the global norm option, which is to designed to remove the different technical barriers between channels, such as due to the labeling efficiency issue or such. So this global normalization, I think Olga also introduced it in the lecture. It just do median normalization across all the channels, all the runs to remove the to make the median all equal. And then this so this now but this global normalization is we need to pay attention is it assume only a small proportion of the proteins. So I think I have let me have a figure here. So okay, we don't have the box plot, but this I think this global normalization, it assumes that for each sample, like across different condition, different group, only a small proportion of proteins are significantly changed. So which means the total amount of material in each sample are equal across all the channels, all the runs. But for some case, but this assumption may be not valid for your own case if you know like maybe more than half or 20 or 30% of proteins will change across groups. Or if your data set does not have a large number of proteins, such as the toy example here, it only have 50 proteins. Then this is kind of almost equal net protein number as the target proteomics. So for such case, we will this assumption is maybe not applicable. So this normalization is not applicable. So for this case, I just set it as a false. Why I said false here is really because the toy example, it has a small number, very small number of proteins. So when you use this normalization, you need to see whether you have a large number of proteins or whether whether only a small number of proteins change in your data set. And that's for the global protein normalization. And then the second one is the reference channel based on normalization. So we already, I think we, for this normalization again is, as Olga said, it requires a reference channel. So it performed on protein level for each protein separately. Then it will equalize the reference channel in each mixture, in each plex to be equalize the reference channel, and then apply the same shift to the other proteins, other channels in the same plex. So this normalization requires you have reference. So you have reference channel in each TMT mixture. So if you don't have it, this is now also not applicable. Currently, MSstatsTMT require the reference channel to perform this normalization. So again, is I think for the normalization channel, we also have, I think, some questions, 2 or 3 questions about how we prepare the reference channels. What I know, because we don't have run a wet lab, but from our collaborators and also papers, most of the cases data set I saw for the reference channel, it's also called master pool channel samples. It usually uses a pool of samples, a small proportion of samples from each sample in the study. For example, in this case, we have let me see, I think it's 120 samples, and then we first digested. In this case, when we prepared, we first digested the proteins into peptides and then labeled and then for the digested peptide, with each sample, from each sample, we select a small proportion. I forgot the percent for small proportion of the peptides and combine them to generate a master pool peptides. That's how we prepare the reference sample here. So basically, in this data set, we just use a small percentage of peptide in each sample and then combine them together as a master pool sample. So and then there's also some option. I think this option usually you don't need to change. Do you want to keep the normalization channel samples in the output, or do you want to keep the empty channel in the output? Usually we just remove the empty channel as the unnecessary channels you don't use. So if we run the this function, you can see this as a message, progress message. So the message actually, if we see one message here, like here, that's for the message for one run. See, summarized for, because as I said, we do the summarization for each run separately. So, and the method we use is MSstats. So it call MSstats for each run. And this is the message when we run data process in MSstats. So this is the case we run for the 15th run and the 15th run. And then that's the summary information, and that's the sample information. And then we also have, and then we have all the message from MSstats. You will see 15 such message because each run has one message separately. And then this message is for protein level normalization. Actually, in the next release, like after our refactoring this message, we will just not just kind of we will put all the message in the log files. Okay, so then let's see the output here. What the file data looks like. So this data set, again, it has run information, protein information, abundance, and the channel, and the bell replicate, and condition, technical replicate, and the mixture. So the abundance is what the protein level abundance we generate. It actually, in this output, what we have is we will have a summarized log2 intensity per protein per run per channel. So, and this is the normalized protein data. So as we did yesterday for MSS tutorial, we can always save this, because this information is what we need. Output we need is a protein level data. So then we can save it as, you can have different option to save. You can save it as a PD, as a R data, or you can save it as a protein CSV file. This is for our reproducibility. You can use it for like a cluster analysis. So we save this file in this. We save the protein level data in the file, in data file, and then it in the protein data, protein of discover and TMT, and here. Yeah, that's the PD and spec in PSM, and PD annotation is our input files. and this is just what we generate. If you open it, open the CSV, you can see that's how the output looks. Okay. I think we also we have a question, another question about the reference channel. So, oh, sorry. So, if how about like this data set, actually it has 2 reference channels, and someone asked, I think some student asked about how we deal with multiple reference channel. Like the example data set, actually it has 2 reference channel. If we have 2 reference channel, when we equalize the reference channel, what we do is we will first average the 2 reference channel. If you have multiple one, we will always average the normalization channel, reference channel in each mixture and each run, and equalize the average the reference channel. Actually, there is not an upper limit for the reference channel. You can, if you have many empty channel, you can use as more as you want. But I say, what my experience is, the performance increase when you use more reference channel is kind of very slight. It's very small, so it's not. I think if you have the empty channel, I would recommend you, if you can put more real samples, not the reference channel. One reference channel is enough for most case. We have I think we already mentioned another question is again about how to prepare the reference channel for label-free and TMT. So reference channel is quite different in label-free and TMT. The TMT is the reference channel is also this reference sample. We will also label it with different isobaric tags. So when we prepare this reference channel, we just combine a small proportion of peptides from each sample in the data set. So like there are 120 for each sample here. This all samples, and for each sample, the peptides of each sample, we just select a small proportion. I forgot, maybe 5% or 6% peptides, and extract and combine those peptides from all the samples and to generate the reference sample. So if that's after we do the protein summarization, we have the normalized protein level summaries. So it's good. We can start to do the group comparison. But before that, we have like MSstats, MSstatsTMT also provide option for the visualization option for quality control, which called data process plots TMT. So in this plot, you have, okay, let's see what does this plot did. It's similar. It's very similar. Like MSstats, it also have many options about the size, font size, the upper limit, lower limit of the data of the axis or y-axis. In this function, I think there are probably these are the important parameters you would like to change for your own data set. First of course, there are two required input, where one is the peptide level data, which is the input of PD, and the summarization level data, which is the protein level data called PD. And then there are tab. So there is first option called tab. In MSstatsTMT provide two types of plots. First is the profile plots, and the second is QC plots. Here we will will look at focus on the profile plot. The profile plot will looks like this one. It will generate a profile plot for each protein separately. So in the profile plot, we have, in this case, it has 15 runs. So we have one panel for each run separately. Each panel here is one run. And the dataset has 15 runs, so there are 15 panels. And inside each panel, we have different lines here. Oh, sorry. Let's start from the beginning. Okay, here. Same as MSStats, we have two profile plot will have produce the two PDF files, two plots. First is the profile plot with all the peptide, all the features, and the second profile plot will plot the protein level summary. So for the first original peptide profile plot, you can see is there are 15 panels for each panel is one run, and within each panel there are different colors. Different colors means different peptides. For this example dataset, it has 22 peptides. And it has a peptide ends, so it has 22 different colors. And then for MSstatsTMT, the plot has also plot different group the samples based on according to different channels. Different groups. So it's maybe small, but you see there. Okay. Let's see. So there are five conditions. 1, 2, 3, 4, 5. Each condition, as in our original design, each condition have let's see. Each condition has 2 replicates. So you see there's five conditions. Each condition had 2 replicates, and then that's the profile plot with the original feature. And then the second profile plot it will generate is profile plot with protein level summary. Again, the gray dots here is the same as the color dots here. Gray dots here is the peptide level data, the feature level data, and then the blue and the red dots here is the protein level summary. This summary is after normalization. So you can see the last 2 replicates is for normalization channel. It's a normalization reference channel, and you see that they are equal across all the runs. How does it look like if we don't apply the reference based on normalization? We have this is the same protein if we don't apply the reference channel based normalization. You see, this is the protein summary without reference based normalization. This normalized the first 2 channels here, they are quite different. They are very different across runs, right? That's why we think the reference channel normalization is helpful here. After we equalize the last 2 data points here, then they become equalize all across all the runs. You can compare. It's the same peptides without reference channel and with reference channel. So we have, I think we have a question is, in this data set, we don't have empty channel. In this data set, we only have a normalization channel. So, okay. So we don't remove any channels here. You can, when you make the plot, actually, you can select. So if you don't want to have the reference normalization channel in the plot, you can just keep the normalization here true. If you want to have the normalization channel in the plot, you can just make it false. So that's how this profile plot looks like. For profile plots, what you can do is you can change, so profile plots, you can change the parameter. So this is the, if we run the profile plot, it will generate 2 PDF files. And this parameter is to change the width and height of the PDF plot, PDF. Because for this data set, it has many runs, so we want it wider, and we give a larger parameter here. And same as MSstats, you can also select which here it will generate a profile plot for all the 50 proteins. If you want to generate only if you want to generate a plot for specific protein, then again, same as MSstats, you can use a parameter which protein and give a protein name here, then it will generate for one specific proteins. So and then again, address here you can change the default profile plot name to whatever you would like to have. So this plot, I think after we refactor all the functions, even currently, this profile plot will take actually the longest time among all the functions because it will generate a PDF with all the proteins. If you have like 5,000 proteins, the PDF will have 5,000 pages. So it takes quite a long to generate it. We save the PDF file again into the data proteome TMT data. And if you look at it, if you open it, it will just give you all the profile plots for all the proteins. It's 50 proteins. And the second one PDF is with the PDF protein summary. You see the summary equal the normalization. So this case, I remove the normalization because when I generate the when I set the parameter when in protein summarization remove normalization channel true, it will just remove normalization, so you couldn't see it in the plot. Okay, now we are going to the last step, which is our most interesting step, is our testing. So we can do the testing function is called group comparison TMT. So if you see this group comparison TMT, it has favor parameters. The first, it requires data from protein level data as input. This course is a quant PD from protein summarization. And then you can specify what you would like to compare in the contrast matrix. This is easier MSstatsTMT provide a keyword called pairwise, so it will compare all the possible pairs between two conditions. For this case, it will we have four concentrations, so it will compare any two concentrations. And if you don't want to compare all the all the pairs of groups, you can specify the contrast matrix like same as MSStats and give a contrast matrix. We have in this tutorial, I will not cover this part, but in this TMT file, this HTML file have all the detailed information. You can refer it, look at it after the class. It include also how to specify a contrast matrix for if you don't want to compare all the possible pairs. So and then the third parameter is moderated, is whether you want to apply the empirical-based moderation, in particular when your sample size is small. So here I set it true to apply the moderation, and then you have the Benjamin Hatchberger adjusted for the multiple comparison. And if we run it, it's the first is fit linear mixed model for all the 15 proteins, and then perform the pairwise comparison for all the 15 proteins. So if you check the output, it will look like this. So it will have protein name. Label is what you compare. Like in this case, first row we compare the group 0.125 to group 0.5. And then the log2 file change, standard error, degree freedom, p-value, adjusted p-value by Benjamin Hatchberger, and issue is same as MSStats. If you have a NA means the protein has no problem, but if sometimes in this, I think toy example is all NA. We don't have proteins with the issue. And we would like to check how many comparisons we perform. So then we can check how many unique labels. Then you see there are 6 unique labels. Because there are 4 conditions, we compare any 2 of the conditions, so it totally 16 compares. And then we can also save this results in R file, R data, or PDF file. If again I save it in the data protein discover TMT, and you can see this test results PD is what you just saved. And all the columns here, you can see. I think we have a question is, so choosing a specific comparison should have more power than conducting all pairwise comparison. Actually, it's not true, because when we adjust for multiple comparisons, what we adjust is for each comparison separately. So if you perform all the pairwise or one specific pair, the adjusted p-value is same, because we always adjusted it for each comparison separately. So we set the default moderated default here as false, because we hope to in 100 people, researchers have more sample size. This moderated works when when the sample size is small. As our experience, when you have more than 5 samples per condition, then this moderation will not make a big difference. But when you have like 2 or 3 samples per condition, then this moderation will help you get a more stable estimation of the standard error. But we set it default as false because we always would recommend you to have more sample size. So that's why we actually set this moderation as false. So then last one, we can also, MSstatsTMT does not provide the plots to visualize the group comparison results, the testing results, but because MSstatsTMT and MSStats, they use this format, this testing results format is same. So you can directly use the group comparison plots in MSStats to visualize the output in MSstatsTMT. So then you can first library MSStats and then output the volcano plot using the function in MSStats to output the volcano plots. So again, we put the volcano plot in the same folder. If you open it, it's the volcano plots. We have 6 comparisons, so we have 6 pages, each page for 1 volcano plot. I've seen here all the significant proteins, differential abundant proteins are UPS proteins, and there are one which has 2 background proteins has UPS protein. So then we can go back to see what happened for these 2 background proteins. But for this case, comparisons, all the differentially abundant proteins are UPS proteins. So this is what we can have. We can generate the volcano plots using this function. So again, for the moderation, we think if you have more than 5 samples, or if you have 10 samples per condition, then this moderation from our simulation results, this moderation with or without this moderation will give you very similar results. So okay, we have as time limit for the tutorial hands-on, we will just end up here. But you can, if you want to have more exercise, then you can go to this, look at this HTML file. It has all the information, detailed information. And in the file, there are two HTML. One is for PD output. That's what we look at here. And all the details and the possible questions. And then if you use MaxQuant, you can look at the tutorial for the MaxQuant, and it will tell you what the required input files and what's the function to run for MaxQuant output. So
Ting, could you show how they can open the HTML file? Where they can see people confuse this one under the folder or link. So they have to download the zip file, right? And then unzip the folder. And then under there, they can find the HTML file, right?
Yes.
And then
so you can, again, the HTML file is, that's the, so here, if you tutorial and click link here, and then there's a zip file. If you download it, you can see, we can really see it. Inside the zip file, there are 2, inside the folder, there are 2 HTML. And that's what you can just click it and it will open in the browser. So I also, actually, I know that what confused it. attach the slides for PD output, the HTML for slides output, HTML file for PD output here. And when you open this link, it's all this code. But if you can click dots here and by download, then you will download the HTML. And if you click on the download HTML, it will just open in browser. So Google Doc has a problem with opening the HTML file. You need to first download it and then just click open. It will open your browser automatically. Okay, so then we have last 15 minutes. I would like to go over the how to prepare the annotation file. So then we will use the second slide, the slide here. You can open it. I will just, okay, let me, okay, and then I will just open. Okay. So in this, okay. Okay, so in this slide, I will briefly talk about how to prepare the annotation file for the 3 data sets. One data set is just a very simple one, which has one run, one mixture, and no fractionation, no technical replicates. It's just one mixture, so one run, and it's very simple. And the second data set, it has two mixtures, but it has fractionations. And then the last one is just the one we use as an example data set. We want to it has 5 mixtures and with 3 technical replicates. I will just introduce how to prepare our annotation file for each case. For one mixture case, this data set actually is a very popular. It's a very popular benchmarking data set published by Paul in 2016. It's a triple, I think, it's a triple knockout protein standard. So there are 3 conditions. For each condition, it knock out one specific gene from the sample. So there are, like you see, there are 3 knockout genes, and then each condition we have 3 biological replicates. So totally there are 9 biological replicates, and then it only need one mixture. It's a non-plexed mixture. In the data set, this data set is published, publicly available. Now it's public. Its raw data is in the proteome exchange, but the real analysis you can also find it in massive quant. Mina will talk about Mina will talk about mass quant tomorrow. But here I just give you the information where you can find the raw data and the intermediate data for this particular data set. And this data set is simple, and it analyzed by we analyze it by PD. We reanalyze it. Actually, this data set was analyzed by many groups, and in our collaborator analyzed it by PD 2.2 for us. For this data set, we inside our annotation file, we always need these 7 columns again. So the first column is called run column, which is the MS run ID. If it's PD output, if you use this PD data, then this run ID should be the same as the spectral file information in the PD file. And the second one is the channel. This is the labeling efficient, like isobaric tag ID, isobaric tags. So if it's 10plex TMT, then it should be like 2126 to 131. It should be the same as the channel columns in the PD PSM file. So these two columns, I will give more details later. Then the condition is quite simple. It's just see what the condition you can see if you have health, cancer, or control tissue. Then it's just the condition information. If the channel has an unnecessary sample or no sample, you can just put empty under the condition to indicate its unnecessary samples. Mixture. So mixture of samples, it tells us, so the concept of mixture is, someone may call it experiment, someone may call it plex, but it's a mixture of samples labeled, each sample in the mixture labeled by a different isobaric tags. And this mixture, we mix all the all the samples labeled by different isobaric tags together. We call this mixture a TMT mixture, and which can analyze by in a single MS run. So technical replicate mixture is sometimes we may, if in order to estimate the technical variation pairs, we may run the same TMT mixtures multiple times through the mass spec to estimate the technical difference. And this technical replicate will just give a technical replicate ID. And the fraction, similar fraction is sometimes in order to increase the protein coverage, we may split. So one mixture into multiple fractions and run each fraction through the mass spec. So the difference between technical replicates. So again, always we run this difference between technical replicate column and fraction is technical replicate mixture column means we run the same TMT mixture, one TMT mixture multiple times, but it's the same one. Fraction is we split the mixture into multiple fractions, and each fraction run through the mass spec. And bioreplicate is just a unique ID for biological subject. So if the channel does not have sample, we just put empty here. Why we have biological replicate? Because sometimes we may have, one patient may generate may have multiple samples like normal tissue, and tumor tissue. So then both of the replicate they from same biological replicate. Like here, here is the dataset example. The run information, the run column, they should be the same as the spectral file in the This is the PD PSM file. PSM file is a peptide spectral match. It's output when we do after the database searching. You search a peptide against spectral against the peptide, and you score each match between peptide and spectral. So PSM is the peptide spectral match, and this run is much same as the spectral file column. You see this in this data set, it only have one run. So all the spectral file column, they have one unique value. So, and this unique value is the run value in the run. And the channel must be the same as the channel columns. And in this case, it has non-channel. So this channel must be same as this column. And this is the final annotation file we generated for this case. Again, it has run run information, same as spectral file column. There's only one run, so we only have one run ID. And then this one run it from the one, this mixture you can get one, you only need to get one unique value because this is only one mixture. So I just still give it file mix. You can give like 1, 2, 3, just as long as it's unique value, one single unique value. And then we don't have fractions, we don't have technical replicates for this case, so we just put one under these two columns. And then condition, there are 3 conditions. And this condition has from, because all the non-replicates are from non-bioreplicate, so you can just give a unique bioreplicate ID for each channel. And the channel, again, you see it's 126 and underscore n, 127 underscore n. That's what I mean. It must the same as the PSM file, because sometimes in the PSM file there is no underscore. There's just 127 and n. So if you put 120n without underscore, MSstatsTMT will return an error because this channel ID is not consistent with the PSM files. That's how I see it. As long you can use the isobaric tag you create in by yourself, as long as this channel ID is consistent with these columns. So we don't pre-define what the channel and the dataset must have. All the channel information is told by the shown in the annotation file. So for the second one, we have fractionations. Again, this is 2 meters. Each meter is fractionated, has 12 fractions. So 1 meter corresponding to 12 runs, and these 12 runs are fractions. And then inside each run, we have 3 conditions. Each condition has 3 replicates, and the last channel is used as normalization channel. Again, this data set is published. You can check the original paper and then the repository for the raw data for the data set, intermediate data set. This data set was analyzed by MaxQuant. Again, because it's MaxQuant for the run ID, the run column, so all the other columns is no, for the annotation, in the annotation file, all the other columns are the same for all the tools like MaxQuant or PD. The only difference is the run and the channel columns. They need to change based on the different tools. For like here, if it's MaxQuant, then the run column must be the same as the raw file columns in the evidence file of MaxQuant. As we know, MaxQuant will store all the PSM like information in their evidence file. Then the input to MaxQuant is the evidence file. What we input to MSstatsTMT is the evidence file of MaxQuant. And then what we need is the raw file column. We need to look at the raw file column in the evidence file, and then make sure the run column in the annotation is the same as this raw file. And the channel, again, it must be the same as the channel columns. Here is 1, 2, 3, 4. So that's the final annotation file we generate we prepare for this data sets. So it has 2 mixtures, and each mixture has 12 fractions, and then there are 24 runs. This data has 24 runs. Each run has 10 channels, and then totally there are 240 rows. So we need to give annotation information for each run, each channel. So then the annotation file has to have 240 rows. Then for each row, we need to give the annotation information. So again, you can see this is run ID, which is the same as the raw file column, which extract from the raw file column in evidence file. And then the channel ID, which is extract from the channel columns in the annotation file. So there are 10 channels. So there's from channel 1 to channel 10. And then for each run, each channel, we give the condition information based on the design. And then this is the design. The first run here, you can see it from the first mixture. Then the mixture ID is mixture 1. Actually, most of the time we can tell from the name that which mixture it comes from. This is it from TMT1, it's mixture 1. And this data set, it does not have technical replicates, so all the technical replicates is 1. I just put a value 1 under all the under technical replicate mixture. But it has fraction. This data set, we say it from fraction 1. Just we label it from fraction 1. So put fraction 1 here. And then the Bell replicates, we see it all different Bell replicates. So give it Bell replicates. And here, another thing we need to pay attention is channel 10 is used for reference channel. Then we just put a keyword norm for reference channel here. So if it's 2 keywords under condition, norm for reference channel, empty for empty channel or unnecessary channel. And then this is the annotation for another run. It's the run TMT2 SF10. You can see again, it's 10 channels. And then for each channel, we have the condition information. And this run it from mixture 2, so TMT2. So we put mixture 2 here. And again, there's no technical replicate, so it's always 1. And this run is the fifth mixture. It's the fifth fraction of mixture 2. So we just put fraction 5 here. Actually, you can. This is the fraction. If you count how many unique fraction for each mixture, then there will be 12 unique fraction ID for each mixture. And then we give the biological replicate, replicate information. So for the last one, I will just very quickly look at the annotation file. Again, it's analyzed by PD. So analyze the PD. So the run information must the same as spectral file in the PSM files. And then the channel column must the same as the channel ID here. Then that's the final annotation file we have. The data set is a control mixture. It has 5 mixtures and 3 technical replicates run. So it totally have 15 runs. Each run is 10 plus TMT. So each run has 10 channels. Then the annotation file should totally have 150 rows. I select the 2 run, the information for 2 run. The first run is mixture 1, 0 and 3. The second run is mixture 5 and 2. So again, it's no fractionation, so the fraction column is all 1. So it's all one single unique value. And then the first this run is from mixture 1, which is the first run is from mixture 1. It put mixture 1 here, and the second mixture is from second run is from mixture 5, and then it should be mixture 5 and the mixture column, and then it's from the third technical replicates of mixture 1, so it's technical replicates column is 3. And then it's a second technical replicate of mixture 5, so mixture technical replicate column is 2. So, and the channel ID is always 10 channels from 122 to 131. It's same as here. So sometimes it has underscore, sometimes it has no underscore. You must make sure they are consistent here. And then fill in the condition and the Bell replicate information. So these two information, we have for each run, we have two normalization, two reference channels, then the two channels are not labeled as null. So yeah, that's how we compared. For this data set, we have only technical replicate, so this change. And for previous data set, we have fraction, so it's fraction column change. So this, if you have both fraction and technical replicates, then these two columns must use these two columns to indicate that. That's how so as a summary, that's how MSTMT work is. In the annotation file, you give all the detailed information about samples, about mixtures. Then MSTMT will automatically detect what the design and the dataset use. And then in the group comparison function, so okay, in the last group comparison TMT function, we will for each protein separately, MSTMT will select the proper linear mixed model. So inside MSTMT, it fixes a family of linear mixed model. I think we fit 5 or 6 different linear mixed model based on, and then based on your design given in the annotation file, MSTMT will select which model it should fit for this particular dataset, particular protein. Because even in the same dataset, one different proteins may have different design if they have due to the missing value cases. So that's why we fit we fit a linear model for proteins separately. That's also one big advantage of MSTMT. You only need to give the annotation, and you don't need to worry what the model you need to fit in MSTMT. Actually, that's also someone I think we had a question about what the difference between like Llama or Perseus or such tools. That's one difference is MSTMT can automatically decide the linear model which should be fitted for the data. But like in Perseus or Llama, you need to specify what the model you would like to fit for the data set. Then the model you specify may not proper for the design. Also, their input annotation information is not as much as the MSTMT allows. So that's why MSTMT, that's how MSTMT works for the statistical testing. Okay. I think that's
Thank you, Ting, very much. This was very extensive and we had a lot of questions answered. And I hope that everyone had a chance to at least try a little bit